Yeah, thank you very much for the kind introduction. The book is also available in German if you prefer reading in German. So I actually helped with the translation since I speak some German too. But we're going to stick with English for today. And yes, I would like to talk about building collaborative software. So things like Google Docs, where you can have several people accessing and editing a document at the same time. You have several users sharing access to some kind of common data set. It might be a text document, it might be a spreadsheet, or graphics, or some kind of database, or file system. Any of these are examples of the kind of software we want to talk about today. And so, as one of my running examples, we'll use text editing, just because it's quite easy to follow. So you could imagine here 2 users who are both accessing a Google Doc. And the content of that Google Doc to start with is hello, exclamation mark. And so we have here time going from left to right. And the users can update the copy of the document in their web browser. And so as they type the letters, the red user here types world, so then the document reads hello world. And those changes are immediately applied to the copy of the document that is in memory in their web browser. And that means that any changes they make are then only sometime later sent over the network to their collaborators. So it could happen that just in the same moment as the red user is typing the word world, the blue user types a smiley face after the exclamation mark. And so then sometime later, it might be just a few milliseconds later, or it might be hours later if they've been working offline. At some point later, these users then synchronize their updates, send their changes to each other, and we need to merge those together. And so if this was Git, you would have to perhaps do a manual merge, resolve the merge conflict. But in the case of Google Docs, actually what happens is that these changes get merged together automatically, and you just end up with the same document on both user screens, with the intention that nobody's edits are lost. And so in this case, we preserve both the insertion of the word world before the exclamation mark, and we preserve the insertion of the smiley face after the exclamation mark, and everybody is happy because the changes have been merged together in a quite sensible way. So this is one example of collaborative editing. We can just take a step back and look at it a bit more abstractly. It doesn't have to be text document, it could be other forms of data, and we can store copies of those data on multiple machines. And those might be end-user machines, or they might be servers. It doesn't really matter for too much here. And then we can have users who access one of these copies of the data and change it. And they make the change to one of these copies, and those changes then get asynchronously replicated to any other copies of that data on other machines. So those changes would be sent over the network in some form or another. And while the red user is accessing the node I, you could have the purple user accessing node J, and they would similarly make changes on that copy of the data, and those operations would get sent to other copies. So in the abstract, we can think of the system like this. In the concrete case of Google Docs, what actually happens is that all of the communication goes via Google servers. And so this has some advantages and some disadvantages. The advantages I will show later in terms of the algorithms for merging the concurrent changes together. The algorithms work quite nicely in the case where we have everything going via Google server. The downside is all of the data is on Google server. So it depends what kind of data you're talking about here, of course. Now, for you and me and most of us in the room, probably the data we're working on is not that sensitive, so it's not really a big deal if we put it on Google servers. But there are people who work on sensitive data, and they are not allowed to simply put their data on the servers of some random company. So you could imagine medical data, which is quite a regulated industry as to where the data is allowed to flow exactly. People have to be quite careful for regulatory compliance reasons. But you could also imagine if you're a dissident in a country with a repressive regime, then keeping your data personal to yourself is maybe actually a matter of personal safety. Similar might happen if you're a whistleblower talking to a journalist, leaking some sensitive documents. Again, it's perhaps a matter of personal safety that your data is handled confidentially. If you work in the legal profession, there are actually special legal protections for communication between lawyers and their clients, for example. And so there are lots of good reasons why people handle sensitive data, and then simply putting it on some cloud server is maybe not the best option. The way I like to think of this is there is no such thing as a cloud, really. It's just putting our data on somebody else's server, on somebody else's computer, And we just have to trust that this computer and the people running that computer are treating the data correctly. So one of the things we are working on in our research is trying to have the same kind of collaboration features like you get with Google Docs, but without having to just dump all of our data on someone else's server. So as we have two users collaborating, here maybe Alice and Bob, and they each have a device through which they are accessing some data, we can do the communication via servers, and certainly that's an option, but it's nice to also have alternatives and not have to do everything via servers. So one alternative might be if the users are actually together in the same building, you could probably use the local Wi-Fi to just send the changes directly between those two users' computers. There is absolutely no need for those changes to go via a server on a different continent in the AWW East, US East region in Virginia or so. It's ridiculous to send our data back and forth over the Atlantic if we don't need to, if we could just use the local Wi-Fi. If the collaborators are not on the same Wi-Fi, we could maybe use a peer-to-peer network, and various people have developed peer-to-peer protocols which do the necessary hole punching, getting through firewalls, getting through NAT, all of that ugly stuff. If the devices are very close together, if it's just synchronizing between your phone and your laptop that are right next to each other, maybe we could use Bluetooth. Or thinking even more broadly, imagine maybe we wanted to build a medical record system for use in rural Africa, where we can't rely on having Wi-Fi everywhere. We can't even rely on having cellular data network everywhere. So outside in the more rural areas in the village, there might not be any reliable way at getting at the internet. But still, we want to be able to synchronize data between the nurse in the village and the doctor in the next town nearby. And how do we do that? Well, it might be that the most sensible communication path between the village and the town is to actually put the data on a USB stick, put the USB stick in the pocket of a guy, put the guy on a motorcycle who drives from the village to the next town. And this is a high latency, but quite high bandwidth form of communication. And the point I want to make with this is just there are many different forms of communication. And really, we want to be able to use whatever form of communication happens to be the most convenient in a particular setting. So being forced to go via servers is incredibly constraining. And if we allow ourselves to just use any communication method, not servers, it opens up all these wonderful new possibilities. So this is what we want. Basically, we want communication without making any assumptions about the network topology. Now we have to do the conflict resolution. That is, if several people edit the document at the same time, how does everybody get into a consistent state? And this is something that people have been studying for quite a long time. So back in the late 80s already, academic researchers started working on this problem of how do you have several people collaboratively editing a document where what you can have, like in the example earlier, is different users' versions of the document diverge slightly because they've made edits concurrently. And those divergent copies of the document we want to bring back together into a consistent state. And so people develop algorithms for doing this kind of thing. And so, for example, this algorithm here, published in 1989, called operational transformation, received quite a lot of interest. Unfortunately, then other researchers looking at it a few years later realized that the algorithm was wrong. And what I mean here with wrong is that there are simply certain edge cases in which the algorithm would remain permanently inconsistent. So like if you happen to do the wrong sort of edit, then two collaborators would be permanently inconsistent with each other and never converge, which is bad because really convergence is the most basic correctness property of what we want to achieve here. So of course people proposed an alternative algorithm and said, oh, well, that one is broken, but this one, it works. Until a few years later, again, somebody realized that that one was also wrong. And so then over the course of a decade or so, there was this whole series, maybe even 2 decades, this whole series of different algorithms being proposed. And then a few years later, other researchers realizing that, oh no, it was wrong, actually. Try yet another one. So this was a really bad time. A few of these algorithms turned out to be correct, actually, surprisingly. But and for example, one of these algorithms that turned out to be correct is called Jupyter. It was published in 1995, and this is the one that Google Docs is actually based on now. However, these remaining algorithms that were correct were only under the assumption that all the communication goes via a central server. So in this case here, the conflict resolution algorithm can operate if we're willing to send all of our updates via Google's server then the Jupyter algorithm can perform its conflict resolution and make sure everyone ends up consistent. But the algorithm does not work if you allow any sort of back-channel communication, any sort of direct communication that doesn't go via the server. Because just the existence of these additional communication channels would undermine the assumptions of the algorithm, and so it would no longer be able to provide its guarantees. So it seems like we're kind of stuck in an ugly place here where we would love to use all of these additional communication channels, but all the algorithms that have been proposed for this kind of network topology turned out to be wrong. So then about 10 years ago, researchers went, OK, we've had enough of this. Operational transformation, which we've looked at since the late 80s, just did not work. It only works in the case of central server. Let's try a completely new approach. And this completely new approach is called conflict-free replicated data types, which is a bit of a mouthful, so we call it CRDTs normally. And that's been around for the last 10 years or so. And this is the family of algorithms that we are now working on. And the nice thing about these algorithms is that they will work in any of these various communication channels. So they don't make any assumptions about there being servers or what the communication topology looks like or what the timing of messages looks like. They will just work in any form of communication. So jumping back to this setting here, where we have several users collaborating, in particular, one of the things that CRDTs allow is for edits to continue even if there is a network partition. So even if some of the nodes, some of the machines in this setup cannot talk to other machines, maybe because this is a mobile device and you are currently in a tunnel underground and you don't have any data connection, so you're offline. And the key point is here, you can still continue making changes to your data even while you're offline, and you would then resynchronize those changes with other users sometime later when you get your internet connection back again. And this, again, is something that CRDTs allow. So CRDTs enable us to have just these different users making edits, even if they're disconnected, and to be able to merge everything together cleanly when the internet connection comes back. So this sounds great, but as I mentioned earlier, there's been all of this history with lots of broken algorithms in the past. So we wanted to be pretty sure that the new algorithms we were developing would not also be broken in the same ways. So we wanted really very strong proof that these algorithms were really correct. So we embarked on an effort, a research effort, to prove some of these CRDT algorithms correct formally. So for this, we used a piece of theorem-proving software. It's called Isabelle. It's formerly known as an interactive proof assistant. It's a bit like a programming language, but for mathematical proofs. And so if you want to, you can prove some statements to be true, and you have to prove it step by step, and the individual steps of the argument, there's some automation which will help do that, but the computer checks every step of the proof, and you literally get an error if the computer can't check the proof. But if you get to the end, that means the computer has told you that the thing you were going to prove really is true, because there's not the possibility of making reasoning errors like a human could, because the computer is checking everything. So what we did was to formalize a couple of different CRDTs. So RGA and RSet and Counter, they're examples of CRDTs. And we wanted to prove that they satisfy a particular consistency model called strong eventual consistency. And the main idea of strong eventual consistency is this convergence idea. That is, if some edits are made over here and some edits are made over there, and then the replicas synchronize, then at the end, everyone converges to the same state. Now, we were able to prove that these algorithms satisfy strong eventual consistency, but we're only able to prove that under certain assumptions. And these assumptions are always where things get dangerous, because if you know the way mathematical proof works, if you make an assumption that is not correct, then your entire proof is completely useless. So you have to be very careful with the assumptions that you make. And in fact, this is where some of the operational transformation algorithms in the 90s went wrong. They came with proofs of correctness, but those proofs made wrong assumptions, and so the proofs were wrong. So what we want to be extremely careful with this, given all of the problems that there's been in the past. So as another level of this proof here, we formalized a computer network in an abstract way. We made a model of a network using just very basic assumptions. So the assumptions here are things like, if you receive a message, then it was in fact sent by somebody. So that's the level of assumptions we make. We make no assumptions about the reliability of the network. So it's OK for the network to just drop all of the messages, or drop half of the messages, or reorder the messages in whatever way you like. All of those things are completely allowed. And what we were able to prove is that these assumptions that we made in the first step, they are always satisfied under all possible executions of the network model. That is, no matter how much the network tries to mess us up, we can prove that under all circumstances, these assumptions will always be true, and therefore that this proof of strong eventual consistency for this data type also holds under all possible executions of this network model. So this is quite interesting, and we won a prize for this paper. I'm not going to go into the proof in any more detail, but if you want to, there's the URL at the bottom where you can read up about it, and it's actually fairly readable for a theory paper. What I want to talk about in a bit more detail is the more practical application of these ideas. So alongside the theoretical proving stuff, we've also been building Automerge, which is an implementation of these ideas in JavaScript. And we've been building a couple of example applications on top of this to test it out. It's open source, of course. I built it together in collaboration with some folks called Ink and Switch, a private research lab. And Automerge you can think of as a library of data structures, essentially. So it's a library on top of which you can build all sorts of different applications. And I will show some examples of applications in a moment. Automerge itself does not assume anything about the network. So it can be plugged in together with communication via a server, or communication via a USB stick in somebody's pocket, or communication via Bluetooth, or whatever you like. So Automerge itself is ignorant as to the network, and then we built a couple of different network adapters to try different forms of communication. But first, talking about the apps that you can build on top of Automerge. So we built a couple of prototypes. One we called Trellis, which is a clone of Trello, the project management tool that you might have used before. It looks like this, our clone. So you've got cards in columns, very much like Trello. So these cards might represent tasks, or in this case, superheroes who are being tried to recruited to a team. And you might have the individual cards assigned to people in the team. You can leave comments on the cards, you can update them, you can move them between the columns, you can change their order, and so on. And so we built this on top of Automerge. So that is an example of a collaborative application. It's collaborative because several people are accessing it. But we can build it without any servers. There's literally no server to this thing because all of the communication goes peer-to-peer, and each user just has a copy of this board on their local computer. So this is the kind of things that CRDTs allow. Trellis is one example. Pixel Pusher is another example application that we built. So this is a kind of retro gaming style pixel graphics editor. So you can make pixel graphics where each pixel is colored in some way. And what we did with this piece of software, actually, was we didn't write the piece of software ourselves. Instead, what we wanted to try was, can we take an existing piece of single-user software and make it multi-user by ripping out the data model in the middle and replacing it with Automerge? And it worked. So we took this thing. It was originally called Pixel Art to CSS, an open source project that's just some person on the internet made for fun. And we took this person's code and modified it and hacked around with it. And originally, it was just this, a single-user application where one user could edit stuff on their local computer and save it to a file. We turned it into a multi-user collaborative application just by taking the internal data structures that were originally just some hash maps and stuff. We replaced them with the Automerge data structures, and suddenly we had a multi-user software, and it actually worked. Another thing that we experimented with this here, you can see here on the side, are different versions of a document. So you might know in Google Docs, there's this feature where you can suggest changes to somebody, and then the owner of the document can decide whether to accept or reject those changes. Or if you use Git and GitHub, you can use pull requests to suggest changes to a code repository. And then again, somebody else can review the pull request and then decide whether to merge it. And so we wanted to experiment with a similar kind of workflow, but what would it look like for a picture, for example? And so what we actually have here is you can create branches in the Git sense of this image, and you can change the data on just one of those branches and see what the picture looks like. And then if you like it, you can merge it back into the master, as you might call it. Or if you don't like it, you can just discard it. And so this was just another exploration of something that CRDTs allow us to do, because CRDTs, as a side effect of their working, they actually capture the version history of all of the edits you make. And so we get actually something that is somewhat like Git, but for all sorts of different data structures and different applications. So Pixel Pusher is another example that we built on top of Automerge. Yet another one, this one we called Pushpin. It's a kind of collaborative pinboard-like software. So in this case, you can take images and text and web pages and PDFs, and you can dump them in here, and you can arrange them on a kind of 2D canvas and move them around in whatever way you like. And you can create multiple boards, and you can share boards with people, or you can just sync the boards between your own devices. And all of that sharing with people or syncing between your own devices, again, that uses the CRDTs. And different people can update their board concurrently, of course, and any of those changes will be merged together through the CRDTs. And finally, another app we built, this one was a tablet app on top of the Google Chromebook platform. For this, we wanted to experiment with handwriting input, and so we used the stylus for pen input on this tablet platform. Again, it's kind of like a pinboard thing, so like a two-dimensional layout. In this case, we allowed you to have boards within boards, and so you could zoom in and zoom out as a kind of spatial navigation. Here, this shelf at the bottom was sort of a way of reimagining copy and paste, and also a way of transferring data between your laptop computer and the tablet, for example. So you can see here, we've done a bunch of experiments around user interfaces as well, which is just as interesting as the underlying distributed system stuff. So those were some examples of applications you can build on top of Automerge. Now looking at the internal details of the implementation, we need to get some kind of communication now. And what we wanted to try here was to do it without servers as much as we possibly could. Not because servers are necessarily evil, but just as a challenge, like to see how far we can get. Because nowadays, if you're building a web application, you just so much assume that you've got a server, it's in a data center, it does access control, you log into that server, and so on. But now, if we don't have a server, we can change all of those assumptions. So like mutual authentication, for example, becomes a totally different thing. Connecting to your collaborators becomes a different thing. So one of the things we tried for collaborators to connect to each other was WebRTC, which is a peer-to-peer networking technology built into web browsers. So this is normally intended for stuff like audio and video calls, but you can send data over it as well. It didn't work very well for us. We had a lot of reliability problems with it. So we moved on to then using a different project called DAT. The DAT project is sort of a peer-to-peer data synchronization library, which is also built in JavaScript. So they've done all of the hard work of figuring out how to get through firewalls and NAT traversal and so on. So we combined Automerge and Hypercore, which is part of the DAT project, to make Hypermerge. So that is the adapter between the peer-to-peer stuff that DAT provides and the conflict resolution stuff and the data structures that Automerge provides. And most of the apps that I showed earlier were built on top of Hypermerge. But of course, if you want to use a server and just communicate via the server via WebSocket or whatever you like, that is perfectly fine as well. So the way you build an application on top of Automerge is you get a data model that is essentially JSON. It's JSON with a few little extensions. And so if you think about what JSON is, like this is, for example, how you might represent a to-do list using JSON. So you have buying milk, which is one item on the to-do list, and watering the plants, which is another item. Each of these items is associated with a Boolean, which tells you if you've checked the tick next to that item. So if you've done an item, you can press the checkbox, which would then change this done field from false to true. And if you think about what is going on here structurally in a JSON document, we've got square brackets, which is a way of expressing an ordered list of items. So whatever you have between the square brackets is some items, in this case the items on the to-do list, which appear in a particular order separated by commas. And then the other structures you have are maps from keys to values, or objects they're called in JavaScript, which are the curly braces. So they will map some key to some value. The key will be a string, but the value could be arbitrarily, could be a nested map inside it, or it could be a list. And you can put these things inside each other arbitrarily. So you can have lists inside maps, inside lists, inside maps, whatever way you like. And so this is a pretty flexible data model. You can build a lot of things on top of it. Automerge, in fact, adds a few little extras. So Automerge adds a text data type with which you can then edit texts character by character. It It also adds a relational table data type, so you can build something that looks quite like a relational database. And all of those things just, they fit into this model quite nicely. And so you would represent the state of your application. Like if you're making a to-do list, this would be your state of your to-do list. You can represent the state using this data model. And whenever the user inputs something into your application, this is reflected by having changes to this data. And so, for example, if I check the item next to a to-do list to mark it as done, that corresponds to the data change of changing the done field for a particular object from false to true. Or you could make other edits. For example, you could change buy milk to buy soy milk. So this would be like a string editing edit. Or you could add a new item to a list. Here, in this case, we want to add an item here in the middle to phone mum. Or you could add a new key into a key value map, or you can update the value attached with anything. Or, of course, you can delete items from maps, or you can delete items from lists. You can edit this data in any way you like. And Automerge captures all of those changes and figures out how to propagate them to the other users and how to merge them cleanly with the edits that other users have made. So in terms of the API, how you use it, it looks somewhat like this. So this is a simple piece of JavaScript. And whenever the user wants to make some change to the application that is on any user input, you would call this automerge.change function. And this is the way how you indicate that some kind of data is changing. What you need to do, first of all, is to pass in the current state of your application, and you get back a new state. And the reason for that is because the state is immutable. So we chose that deliberately for various reasons. One of the reasons is that it makes it play nicely with React. So if you do any user interface development with React, you will be familiar with this sort of immutable state idea. Also, it just makes a lot of the concurrency handling in general much easier. So that works. Whenever you want to make some state, you have to pass in the current state. Then within this stuff here, you can make changes, and then you get back the new state, which reflects those changes that you've made. And then based on this new state, you can re-render the user interface of the application, and thus you get the user interaction. So you pass in the current state. The second thing you can pass on, if you want, is an optional message. So this is, think of it like a commit message in your favorite version control system, where if you commit, you can typically add some kind of human-readable message just describing the change. This is very much the same kind of thing. So the text, it's not interpreted in any way. This is just for any humans inspecting the change history, because we do actually capture the entire history of all of the changes that have happened here, very much like a version control system. So this just allows you to describe what it was that the user did. And then finally, we have this callback function here. And within this function, you get an object, doc, which stands for document. And within this function here now, you can make changes to the document. And you can make changes just using any of the typical JavaScript operators or methods that you might be familiar with. So while the state itself is immutable, just within this block here, it suddenly becomes mutable, just for the period of this block. And so, for example, I can do doc.todos, which is the array of items in the to-do list, and I can call .push, which is the JavaScript method for appending a new item to the end of an array. And so this is how I would add a new item to the end of the to-do list. I just call todos.push and pass in the new item that I want to add as a simple JavaScript object. And this is all that's necessary. So it's a fairly intuitive programming model. And what Automerge does under the hood when you do this is when you call one of this function, Automerge actually changes this, turns this into a log of operations. And these operations describe exactly in little steps what every single data change is that happened in the process here. So the data change is that we create a new map object, so the curly braces. We set the title field to the value by milk. We set the done field to the value false. Then we reserve a new position in the list of to-do items, associate that with some ID, and then we link this newly created object into the list of to-do items. So as a user of Automerge, you never have to worry about this log of operations. This is just purely an internal implementation detail. But I wanted to show you just so that you get an idea of what is actually going on here. Because then when you have multiple users or multiple devices which want to sync up their data, what you send is not the current state of the application, but what you send is this log of operations. And so these operations get packaged up in a message, get sent over the network, and at the other end, the receiving end, those operations then get applied to the copy of the document there. And the guarantee that we provide, which is what makes this whole thing work, is the following. whenever you have two users or two nodes or two devices which have seen the same set of operations, then they will be in the same state. And this is true even if they receive the operations in a different order. So no matter in which order you receive the operations, once you've got the same set of operations as somebody else, then you will be in the same state. And that is the essential convergence guarantee that we need here. Because, for example, if I make a change on my copy of the data, that means I apply my own operations first. Then somebody else makes changes. They will apply their own changes first. Then we send our changes to each other. So I will apply my own changes first and the remote changes second. The other user will apply their changes first and my changes second. So they're applying the changes in the opposite order, but we will nevertheless end up in the same state as long as there's some form of communication that eventually happens here between the users. So this is very nice. Let's look at some examples of how this kind of merging and conflict resolution might look like in practice. So here we've got two users, one on the left, one on the right. They start off in the same state. They've got a to-do list containing one item, watering the plants. Let's say on the left-hand side, we add buy milk to the to-do list, like we had just now. And on the right-hand side, the first item in the to-do list, the done field, gets set to true. Okay, so you can see what the effect of these changes are. On the left-hand side, we push this item to the end of the list. So now my list contains two items with buying milk as the second item. On the right-hand side, there's still only one item in the to-do list, but its done field has been changed from false to true. So this is the local change, and now network communication happens. We send the data via whatever communication channel we have, and we need to merge those changes together. And in this case, the merge changes, what we want is reasonably obvious what we would want. That is, here on the right-hand side, this adding the buying milk has been added as the second item in the to-do list while the first item remains unchanged. Here on the left-hand side, we already had this second item in the to-do list, but here now this field, done field on the first item has been changed from false to true, while of course the second one still remains false. And so in this case, there's like obviously one way of merging these things. There's not much to argue about really here. There's a trickier case in which we can't actually do the merging automatically. And this case happens if two users concurrently update the same property of the same object. And so, for example, one user changes the title from buy milk to buy soy milk. Another user changes it from buy milk to buy almond milk. And now in this case, Automerge can't decide which of these two values is more correct than the other. They're both equally valid values that were assigned to this field. So in this case, we actually just keep both of the values. So we pick one of the two by default as the standard resolution, and we just use an internal mechanism to make sure that the standard resolution is the same on both sides. So for example, here buy soy milk was picked as the default resolution, and both will have the same default resolution. But the buy almond milk is here available in this conflicts object on the side. So you can then decide as an application if you want to surface this to the user in the user interface somehow, as to choose, or maybe you know from some kind of context that actually it doesn't matter, you can just throw away one of these values. So that is up to the application to decide then. But it turns out actually that if you have a JSON data model, this is the only case in which we have to surface the conflict to the user. So the only case where the conflict really arises is two users updating the same field in the same object. All other cases are actually merged together automatically. So you can add items to lists, you can remove items from lists, you can update keys in maps, you can remove keys from maps, and so on. You can move things around even, and all of those things will be merged cleanly. The only thing that really we have to do manually, because there's no sensible alternative, is this one case here. So I thought in the remaining time I might show you how one of the algorithms works internally, because it's kind of cool and it's interesting to see, and it also gives us a comparison to Google Docs. So just give me 1 second. So I'll do an example of text editing. And we have two users, one on the left, one on the right. And let's say we start off with a document that contains 4 letters, H-E-L-O. And we will treat this simply as an array of characters, and so we'll give each of the letters an index from 0 to 3. Both start off in the same state. And now one user edits this document and adds the letter L here, and the other user edits the document and adds an exclamation mark at the end. And so these are two concurrent edits, and we want to be able to merge them together. And so I now will show the way that Google Docs handles this particular case. So as you remember, Google Docs goes via a server. It uses an algorithm called operational transformation, and you will see in a moment why operational and why transformation. So operational because the stuff that gets sent via the server are operations, and the operation describes what change you made where in the document. And so in this case here, the left user inserted the letter L at position 3, or at index 3 in this document. And so as you can see, the letter O moved on to index 4, because we inserted the L at index 3. And then on the right-hand side, we insert the exclamation mark at index 4, so at the end of the document. And so both users will send their changes to the server, and the server needs to forward the changes to the other user so that everyone at the end has the same document on their screen. So for example, the green change from the left-hand side will get directly forwarded to the purple user on the right. So the insert L at position 3, you can apply that. You can look at this document here and say, OK, position 3, that's currently the O, so I'm going to move the O exclamation mark along by 1. And so at position 3, we insert the L, and we get hello exclamation mark with 2 L's and the exclamation mark. So that looks good. This is what we wanted. Now move in the other direction. So we take this insert exclamation mark at position 4, and look at what would happen here. Now, if I just take that operation here and insert exclamation mark at position 4, what I would get is hell exclamation mark O. So it would insert the exclamation mark before the O, because that's where position 4 is. So really what we have to do is we have to change the position 4 to position 5, because this user here has inserted a letter before that other insertion position. And so any concurrent insertion that comes from the other side will have to be moved along by 1, otherwise it'll end up in the wrong place. So here, the server has to do this transformation. It has to figure out that at the time when this insertion of at the time when that insertion of the exclamation mark was done, that exclamation mark did not know about the insertion of L, and so therefore the insertion of exclamation mark has to be transformed with respect to that insertion of L. So the exclamation mark insertion has to be moved along by 1 so that it's then inserted at position 5, and then the exclamation mark ends up in the correct place, and both users end up with the same document, hello exclamation mark. So this is why it's called operational transformation, because these indexes here have to be transformed by the server. This is also bad news for us, because it means all the communication has to go by the server, because the server has to do this transformation task. It's also bad news if we want to do any encryption here, because it means we can't encrypt these messages because the server's got to manipulate them. So this concurrency control algorithm fundamentally assumes that we have to trust the server. And so this is what we're trying to get away from. So let me show you how you would do the same thing in, yeah?
How do you deal with the problem that there is a delay in sending this insert L at position 3 and getting back the position 5? Because during that, you might have edited again and put another letter in, so that position 5 is no longer correct by the time you receive it on the client side.
Exactly. So what happens is that the server and each of the clients maintains what is called a history buffer, which keeps track of all of the changes that have been made by the local user but not yet acknowledged by the other side. And then whenever you have an incoming change, you have to transform the incoming change with respect to the entire history buffer. And so these algorithms get...
So you have the entire algorithm again on the client that you have on the server for the conflict resolution?
Yes, you need more logic on the clients as well, exactly. You can reduce the logic on the clients in some cases, for example, if you're willing to have just a single message in flight at a single time. So if you don't pipeline the messages, that simplifies it a bit, but it's still pretty hairy. And imagine generalizing this to not just a text document, but a rich text document, or making a spreadsheet or something like that. The algorithms really get hairy pretty quickly here. And operational transformation has a reputation of being a nightmare to implement correctly, because there are just so many cases that you have to get right. And that's why so many of these algorithms were wrong in the past as well. So a CRDT uses a different approach. A CRDT for text works by giving every single character a unique identifier. Now, this sounds inefficient, but there are ways of optimizing it, which I won't have time to talk about today, but just assume for now that we can just associate a unique identifier with every character. And this unique identifier is going to consist of two parts. Firstly, a number, which is here somewhere between 0 and 3. And secondly, a letter here, which is actually an identifier of the device that produced this particular insertion. And so I've got node A on the left, node B on the right. So any insertion that is produced by A will get an A as its letter. Any insertion produced by B will get a B as its letter. And so we assume that each device has a unique ID. This might just be a UUID or the hash of a public key or something along those lines, something that uniquely identifies a particular device. And what we will do if we need to generate a new identifier is we will take that device ID and we will combine it with a number. And that number is 1 greater than the greatest number we have so far in the document. So here, the greatest number we have so far is 3. So when we want to insert this letter L here, we will give it a number of 4, because that's 1 greater than the greatest number we have so far. And the letter we attach to it will be A, because that's the name of the node that produced it. And so this 4A here will be a globally unique identifier, because the A is uniquely identifies the device, and the number uniquely identifies the operation within the device, because it's always incrementing. And on the right-hand side, if we insert the exclamation mark, it gets an ID of 4B, because it applies the same rule. So we pick 1 greater than the greatest number we have, so 1 greater than 3 is 4, but we attach the node identifier B to it. And so we give each edit a unique identifier, and that unique identifier becomes the identifier of that inserted character. And so now we can send the operations, again, via the server or some other communication channel, and those insertions talk about IDs rather than talking about indexes. Because if you remember with operational transformation, the whole problem was we said inserted index 4, and then the meaning of that index changes depending on what other people are doing. But the unique identifiers of our characters don't change. They always remain the same for the lifetime of the document. And so therefore, we can say this insertion of L with the new ID 4A, we insert the L after 2A. So 2A is that first L, so we put the second L after the first L. And so we use this ID to identify the position at which we want to insert. And likewise, on the right-hand side, we insert the exclamation mark. It has a new ID of 4B. We want to insert it after 3A, because 3A is the ID of the O. So this works quite nicely now. We can take this message, and the server can simply forward it over to the other side. And so on this side here, we have this forwarding of insert L with ID 4A after ID 2A. 2A still is the first L there, so we insert the second L after the first L with ID 4A, and we end up with the document that we wanted. Now go in the opposite direction here, the exclamation mark. We again take just that same message, insert exclamation mark with ID 4B after 3A. 3A is still the letter O, so we put the exclamation mark after the O, and everybody is in the same state. Isn't this beautiful? And in this case, no transformation had to happen. The server only had to forward the messages. And in fact, now the server is not special anymore. It's just acting as a store and forward message broker. So in fact, we could send these operations via any communication channel, and it would still work. So there's one edge case here, which I've not yet explained, which I'm wondering if anyone here can spot that.
Well, if both parties insert after 2A, for example.
Yeah, if they insert at the same position, exactly. If they insert at the same position. So I'll give a new example here. In this case, a document is ABC, and on the left-hand side, I'm going to have a user insert X and then Y between the A and the B. And on the right-hand side, I'm going to have the user insert P and Q also between the A and the B. So the sequence of X, Y, and PQ are being both inserted at the same position. And we want to make sure that even in this case, everybody ends up with the same document at the end. So in particular, I expect the document to be either A, X, Y, PQ, BC, or A, PQ, XY, BC. So the XY and the PQ will always be between the A and the B, and the relative order of A, B, and C won't change. But whether the XY comes first or the PQ comes first, there's no way of knowing, because this is symmetric, so it could be either way around. So let's say we first take this insertion of P and apply it on the left-hand side. So the operation is going to look exactly like before, and we're going to generate identifiers for each of these characters as before. So the P here is going to have an identifier 4B, like we had before. The 4 is 1 greater than 3. And we're going to insert it after 1A, because 1A is the identifier of A. And so the P with identifier 4B gets put directly after the A here. And then the second insertion, the Q gets an ID of 5B. Again, the number is 1 greater than before. So the insertion of 5B comes after 4B. it can just refer to the last letter that it just inserted, so the Q gets put after the P, and this works. Okay, but now what happens in the other direction? So now we want to take these insertions of X and Y and insert them on the right-hand side. And so note now, if I just take this operation here, insert X with ID 4A, same ID as before, after 1A is the A. If I just take that directly, then I will put the X immediately after the A. So then I would end up here with AX PQ, and this would be bad because here we've got the PQ first and the XY second. So we have to somehow make sure that the X also ends up after the PQ on the right-hand side. And in order to make that work, we rely on a little trick. And so that trick is to look at the identifiers involved here. And there was a particular reason for why I chose the identifiers the way I did, because we can compare them now. And what we're going to do here is, when this insertion here, this operation comes in, insert after 1A. So we'll first search for the insertion position, 1A. OK, that's here. We'll start at our insertion position here and assume that we put it directly after the A. We will now compare the newly generated identifier. This is 4A. We'll compare it to the identifier of the character that is immediately to the right of the insertion position. And what we will do is, if the character immediately to the right is greater than the incoming character ID, then we will skip over that character. And the way I define comparison here is as follows. We first of all compare the numbers. In this case, the numbers are both 4, so they are the same. Then we compare the node IDs second. And in this case, the node IDs are B for the 4B, and it's A for the 4A. And so I'm just going to say B is greater than A. We can define any sort of lexicographic ordering or whatever we like here, anything that's, as long as it's a consistent ordering on the node IDs. And so because 4B is greater than the incoming operation, I'm going to skip over it. I'm going to keep skipping over any IDs that are greater than the incoming ID. So 5B, well, that's definitely greater than 4A, because the 5 is greater than 4. So we skip over the Q as well. Next one we try is 2A, and our 2A is less than 4A. So now we stop skipping. So at this point, we've now found the position where we want to insert. And this algorithm actually works. It's maybe not entirely obvious why it works. But I'll just finish it. Actually, the last case is the insertion of Y. So the insertion of Y is insert the Y with ID 5A. That's the new ID after 4A, which is the X. So this is easy again. Now here we just have the 4A. We put the 5A directly to the right. You had a question at the back?
Yeah, understood. But where's the difference to the conflict case that you've given before, where the buy milk was edited in parallel by two persons?
Mm-hmm.
And there was a word added in between. Forgot the details there, but word was in both cases edited in between. There you said that's a conflict.
OK.
This isn't a conflict.
Yes. The question is whether you want to treat a string as an atomic value or treat it as a sequence of characters. And in Automerge, you have the choice of both. So in the case of some cases when you're editing a string, you might not want to merge the strings together in some way. You might want to actually keep them as discrete values. For example, this would be the case in JavaScript. In JavaScript, we don't have enums. So if you want to represent an enum, you would typically pick a string from a fixed set of strings. And so in that case, it doesn't make sense to merge them together. You just want to treat them as values and have either this value or that value. Whereas if it's a text, then you'd want to treat it as character by character edits. And so it depends. So in the case of the soy milk and almond milk, you're right, you might well represent it as text. And in that case, these insertions would get merged together in this principle. So it's a choice whether you want to treat it this way or that way. I should probably change that milk example because it's a bit confusing.
But you would end up with by almond soy milk.
That's right, exactly. So either by almond soy milk or by soy almond milk. So the order, again, would be arbitrary. So yes, then.
That wouldn't make sense at all.
Yes, there are even harder cases. So yes, we're not trying to do conflict resolution at some kind of human language semantic level. That would be unachievable. In principle, you could try to detect are two users trying to correct the same spelling mistake in the same word and try to merge those together in some clever way, I regard that as a can of worms that is just not worth opening. And as a second argument, just to higher authority, basically Google Docs does the same conflict resolution, and people seem to live all right with it, so it's probably okay for our purposes as well.
So would an application running based on the status structure now, it basically say something like, I recognize this as some sort of conflict state because there are multiple characters that have the same numbers and formatted in a different way, and then you would still have some form of resolution step where you're, for example, changing the 4B and 5B again to something like 6B and 7B, or
no, so you should
you leave it in this state?
You just leave it in this state, so you never change the IDs once you've created them. And it's perfectly fine to have multiple IDs with the same number.
That's fine, but you might still want to highlight this as a critical case, right? I mean, you
yes.
might not just sign, and that's why I was asking. Like, if you start highlighting it, then the user may specifically sign off on it, and at that point you might want to increment the identifiers again to make clear that you've resolved it.
Yeah, I think you would probably use a different signaling mechanism to say the user's confirmed it, but yes, something along those lines would be useful. I don't know of any applications currently that actually do that. It would have to be a bit of a heuristic because you want to not just find places where you're inserting at literally the same position, but you might be interested in insertions that are within a sentence of each other, for example, or something like that. So I think it would depend on the application to define what the right heuristic would be in that case. But yes, having some kind of alert to the user that, hey, somebody else changed something close to you, you might want to just go and look that it's okay. That would be a useful feature to have, definitely. Yes, please?
So how would you like deal with like actual formatting? Like, say I want to make something a link, right? Would I have like basically two insertion points before and after like the text that should be a link? Or would I like replicate like the information, this character is a link on every single character individually?
I would probably do it as having a marker at the beginning and end of the link. Like in principle, you could use HTML or Markdown or something like that, although what I'd probably do is use some kind of out-of-band markers, so like use an actual object type or so that tells you the start and end of spans for a link or bold or italic or whatever it is. Then there's a question if you have a more like tree-like data structures, because you can have lists of bullet points with nested list of bullet points, that in general becomes a tree, so you could represent that either by sort of start and end markers for each bullet point, or by having an actual tree structure, because JSON gives you trees. So both are possibilities there. Do you?
I found the idea of reducing the number of required indices intriguing, and I thought of Patricia tries, and then I thought I was being smart, and then I quickly realized that this ends up very, very quickly in a mess. So in easy words, what solutions currently exist, or what solutions are you currently working on and thinking about that could reduce the number of necessary indices?
So you mean all of these unique identifiers here?
Yes,
Yeah.
yes.
Yes, so what some researchers have done is propose versions of this algorithm where you insert entire chunks of text in one go, and then you give just the entire chunk a unique ID, and then you can use indexes within the chunk. But then you have the problem that you have to break those chunks when somebody inserts something in the middle of it. So the algorithm gets a lot more complicated then. So my preferred approach to this is actually to keep this conceptually simple model where each character has a unique ID, but to compress the IDs. And so by choosing a suitable compression algorithm, I think we can bring down the cost per character to actually just like 1 or 2 bytes per character of overhead.
Exactly the example that you've given was the one that came into my mind, and I think the problem is, for example, when you think you insert ABC as a whole, so then you say, okay, 1A. Now you need, person A wants to insert something, he needs to split up the ABC and make 1A to, well, in this case you would need 3 indices possibly, and then the person on the right-hand side would want to do the same. So then I think the problem starts already with the number of, with the choice of numbers of indices that you do, because if you say, okay, I split 1A into 1A, 1B, and 1C, and the person on the right hand does the same, so really you also have to define an order for this.
Yeah, exactly. I haven't looked at those papers super detailed, because I personally think it's the wrong approach, because the algorithm gets so hairy. So I think the compression is a much more productive approach here. And the compression can actually be fairly simple. So observe that if you insert a sequence of characters one after another, their node ID is always the same because they've come from the same device. And their number part of these IDs is just an incrementing sequence. And so you can delta encode and run length encode these things, and they compress down to almost nothing just by using the type of typical access patterns that people have while writing a text. So you tend to get these increasing runs of identifiers, which then gets interrupted at some points, but the runs are long enough that that you can get some really good compression there. So yes, this is almost the end. To quickly finish off this idea with the jumping over things that I talked about earlier, I just wanted to show you that it does in fact work. So here, for example, with the insertion of this 4b here, I won't jump over 4a because this is less, and I would skip over only any items that are greater. And similarly here, with the insertion of 5b, I won't jump over 4a. And so that's why the scheme for assigning these identifiers is important. That's why I had to pick the number as being 1 greater than the greatest so far, because that ensures that any character to the right of the newly inserted character will have a lower ID always. And so that is the consistency property we require here. And so this algorithm here, it's called RGA. It has the nice property that it doesn't require a server, but we can just send the edits via any kind of network. And yeah, I think that's pretty much all I have to say, so we're out of time. If you're interested in more, there's lots of details on these various links about all of the various software projects I showed you are open source if you want to tinker around with them. Obviously, Automerge is open source. We've got a few academic publications which describe the ideas in some more detail. So yeah, thank you very much for coming.